Welcome to another time value of money video. We're going to work on problem number 11. And number 11 refers back to problem number 3. So let me go real quick back to number 3 for you. And number 3 says the idea is you're going to fund your child's education. You're going to make deposits at dates 1 through 17, and you're going to pay tuition at dates 18 through 21, and we did that in great detail. So this is the problem that this is referring to. So let's go back to number 11. And in problem number 3, we were dealing with annuities, and what problem 11 really does is turn these annuities into growing annuities. Okay? So consider the information provided number 3 above. Now suppose that only the date 18 tuition payment will be $30,000, and that at each of the subsequent tuition payments will be 10% greater than its predecessor. Further, suppose you do not wish to make equal-sized annual deposits. Rather, you desire to increase the size of your deposits by 5% each birthday. Considering these modifications, what must be the size of the deposit that you make on the child's first birthday? So we want to know the first deposit size. Okay, so when we're modeling this, what we really have is a cash flow date line that looks like this. Nothing happens at date 0. Child's born, I guess. That's a big deal, I guess. And here we make some deposit D. And now what we're saying is the deposit at date 2 is D times 1.05. Deposit at date 3 is D times 1.05 squared, and so on. All the way out to date 17 when we make the last deposit. And the deposit then would be D times 1.05 to the 16th power. Okay, and the idea is then at date 18, we make a tuition payment of $30,000. So from the perspective of the account, it's negative. Okay, and then at date 19, we make a tuition payment of minus 30K times 1.1. And then I'll go down here for 20. At 20, minus 30K times 1.1 squared. And then at date 21, minus 30,000 times 1.1 cubed. Okay, so that's the plan here now. So the question is solve for D. And what we see here is that we have 2 growing annuities. Obviously, this is our first growing annuity, and this is our second growing annuity. Okay, and so the neat thing about our multiple cash flow stream present value interest factors is that they always give us the value 1 period prior to the first cash flow. So if we use a present value interest factor for a growing annuity and apply it to the deposit growing annuity, it'll give us the value 1 period prior to the first cash flow. First cash flow is at date 1, so it'll give us the value at date 0. And then we can solve for D if we state this tuition payment annuity at the same date. So if we initially apply a present value interest factor for a growing annuity to a tuition payment growing annuity, it'll give us the value 1 period prior to the first cash flow. The first cash flow is at date 18. 1 period prior is date 17. Then we're going to need to use a present value interest factor to get that all the way back to date 0. Okay, so let's see how this works. So we're saying that that deposit times a present value interest factor for a growing annuity, where R is equal to 0.14, and N is the number of deposits. That's still 17. And of course we have G, the growth rate, and that's 5%, decimal 0.05. And D times that present value interest factor of a growing annuity gives us the value at date 0. And that is going to be equal to 30,000. which is the size of the first tuition payment, multiplied by a present value interest factor for a growing annuity, where R again is 0.14, N now is 4, because there are 4 payments, 4 cash flows in this tuition growing annuity, and the growth rate is 10% or 0.1. And that's going to give, when I multiply this times this, that's going to give us a date 17 value, one period prior to the first cash flow at date 18. So then I have to multiply this by another term to get us back to date 0. Okay, and the other term that we multiply it by, of course, there's the multiplication sign, and I'll just kind of put it down here. I have to multiply that by a present value interest factor, where R, of course, is the opportunity rate of return is still 0.14, 14% per period, and N equals 17. You'll remember once again that the value for N for present value interest factor is the number of periods we're moving back in time, and we move a single cash flow or a lump sum value back in time. When we multiply our growing annuity first payment $30,000 by this, it's going to give us the date 17 value as a lump sum value. So we're perfectly good to multiply that by this PVIF. So let's see the arithmetic and the algebra and how they apply to this now. Okay, so we can see that we're going to be left then with D times 1 over R minus G times 1 minus 1 plus G over 1 plus R to the nth power is equal to 30,000 times 1 over R minus G, and this is this G here is the growth rate of the tuition growing annuity, so I'll give it a subscript, times 1 plus G sub T over 1 plus, oops, I'm sorry, I forgot the 1 minus, so there we go. Start this again. So I have to then go 1 minus, and then 1 plus G sub T over 1 plus R to the N, and I'll put a subscript on the N now, sub T for the tuition growing annuity, to distinguish it from this N here. And then that's multiplied by our present value interest factor, which in this case, I just go right to what it is. It's going to be 1 over 1.14 to this, oops, to the, I'll tell you what, I'll erase it again. I'm having a little trouble with this. There we go. Times 1 over 1.14 to the 17th power. And that's our problem. And now we'll plug in all the values. So we've got D times 1 over 0.14 minus 0.05 multiplied by 1 minus 1.05 divided by 1.14 to the 17th power is then equal to 30,000 times 1 over 0.14 minus 0.1 times 1 minus 1.1 over 1.14 raised to the 4th power, and then this term multiplied, of course, by 1 over 1.14 to the 17th power. Okay. Of course, you see that D then is equal to this entire side over here divided by this. So I'll just write that out for you. So D is equal to 30,000 times 1 over 0.04 times 1 minus 1.1 over 1.14 to the 4th power times 1 over 1.14 to the 17th power. Okay, divided by 1 divided by 0.09 times 1 minus 1.05 divided by 1.14 to the 17th power. And that'll give us the value of D, the first cash flow that we make at the child's first birthday at date 1. And if you want some numbers here, you get 30,000 times 3.3284 times 0.1078 divided by 8.3658, and that leaves you with $1,286.67. So that value, $1,286.67, is the amount of the deposit at date 1, 1286.67, and the deposit at date 2 would be 1286.67 times 1.05, and so on. And that's the answer to number 11. Thanks for watching.